In this last section, we're going to be talking about natural frequency, driven oscillations, and resonance. The natural frequency is defined as the frequency at which an oscillating system will naturally oscillate if released and then left alone. This frequency depends, as we know, on the properties of the system. Recall our mass on the spring. F0, and we add this little 0 here to denote the natural frequency, depends on the stiffness of the spring K and the mass m. You might recall we write this as the angular frequency, which equals the square root of K, the stiffness, on m, the mass. We can also write this as the angular frequency equals 2 pi f, so f0 equals omega on 2 pi. Again, this little naught here is added to make it clear we are talking about the natural frequency. This is the natural frequency for a mass oscillating on a spring. So an oscillating system doesn't have to be left alone. Of course, we can interfere with the oscillating system and we can drive it. An oscillating system can be pushed or driven by an external force. An example of this is the gears or the spring system that powers a grandfather clock. If a system is driven, i.e. it's pushed or pulled by a separate external force, at a frequency equal to f0, the natural frequency, then an effect called resonance can be seen to occur. Let's plot this to visualize this effect. An external force is used to drive a mass on a spring at a range of frequencies. The natural frequency of the system equals 2 Hz. So if we plot here the amplitude as a function of the external frequency, we can see what happens when we drive this system at a range of different frequencies. At frequencies away from the natural frequency, there's not much response from the system, but as we get closer to 2 Hz, which is the natural frequency of the system, we can see that the amplitude increases. The maximum amplitude is seen as the frequency of the external force equals the natural frequency of the system, and this is defined as resonance. At the right and the left edges of this plot, we can see that the driving frequency is substantially different to the oscillator's natural frequency. The system oscillates, but its amplitude is really quite small. The system does not respond well to a driving frequency that differs very much from the natural frequency f0. As the driving frequency gets closer to the natural frequency, the amplitude of the oscillations rises dramatically. This large amplitude response to a driving force, whose frequency matches the natural frequency of the system, is called resonance. Within the context of driven oscillations, the natural frequency is often called the resonance frequency. The amplitude can come very large when the frequencies match, especially if there's very little dampening. Let's plot an example. We'll show the response curves of an oscillator with different amounts of dampening. We can plot here the amplitude versus the frequency, and we'll plot 3 different types of dampening. A system that is significantly damped, up to a system that is lightly damped. You can see that the lightly damped system, we get a tall and narrow response, whereas a system that is significantly or well damped has a much smaller response, but it's also wider, so it responds over a larger frequency range.